Welcome back. These slides are from Tore Dubois, who works at the University of Oulu and SINTEF. And 6 years ago, in ESM conference, he presented this rather interesting paper titled "What Works for Whom, Where, When, and Why?" on the role of context in empirical software engineering. Now I will use his slides to share some insight about software engineering context. In the figure, you can see that we can have technology, such as a helicopter or a bicycle, and then we have some outcome of this technology. However, the outcome of this technology is not straightforward, but it is influenced by the context. In software engineering, we wish to understand which technologies cause which outcomes in which situations. For example, when is technique X more efficient than technique Y? What resources are needed to use method X in a given situation? How to tailor process X to the actual situation? In software engineering context, these technologies can be processes, tools, practices, or anything that you consider to be improving software engineering productivity. What is context? It has several meanings. The origin, contextus, from Latin means weaving together or to make a connection. In linguistics, it means how readers can infer the meaning of a passage by referring to its intratextual clues, something that transcends the text itself. For software engineering, the definition from management is the most relevant. In management, context means the circumstances, conditions, situations, or environments that are external to a specific phenomenon or technology and that enable or constrain it. An example. So we consider what is best, pair programming or solo programming. To investigate this, an experiment was done with 295 junior, intermediate, and senior professional Java consultants from 29 companies. These consultants were paid to participate in an experiment lasting 1 workday. From the consultants, 99 individuals were formed and 98 pairs were formed. The pairs and individuals performed the same Java maintenance tasks on 2 different types of system, one being a simple system with centralized control style, and another one being a complex system with delegate control style. The researchers measured duration, effort, and quality of the solutions. Here we can see the total effect of pair programming. We can see that the duration is 8% less, meaning that the pairs were 8% faster than the single programmers, which is positive. We can also see that correctness was 7% higher. This is also very positive for the pair programmers. Unfortunately, since pair programmer takes 2 programmers, where a single programmer only takes 1, we can find out that the effort was 84% more for the pairs as 2 people were needed. More detailed analysis shows that the effect of pair programming for junior programmers were different from the average. We can find that the duration in pair programming was increased by 5%, which is negative. We can also see that the effort increased by 111%. But in comparison to the average, we can see that the correctness for juniors was improved 73%, whereas in total the correctness was only improved by 7%. So, for juniors, when pair programming, they spent even more effort and had higher duration. However, the correctness was vastly improved. An additional factor of system complexity is put on the slide here. We can see that for juniors, the duration and effort are not really dependent on the system complexity. So we have in the blue color CC an easy system, and with the red color we have DC, which is the complex system. For correctness, we can, however, see that for the complex system, the improved correctness of pair programming was much higher. What we can conclude from here is that when juniors are building a complex system, then pair programming is probably a very good idea, because the improved correctness is much superior for the pairs compared to the single programmers. For seniors, things look a bit different. We can see that the duration was reduced by 9% in pair programming. Again, the total effort was increased as 2 people are needed in pair programming compared to solo programming. But what was surprising is that correctness also decreased in the pair programming condition. When we add in the system complexity, we can see that there are differences. When the system gets complex, the pairs in seniors use longer duration, they also use more effort, and their correctness improves, but it is still negative compared to solo programmers. So here is a summary table showing when should pair programming be used based on this experiment. It should be used for junior programmers with any type of tasks, provided that increased quality of the task is the main goal. It should be used for intermediate programmers only in complex tasks, provided that increased quality is the main goal. For expert programmers, you should not use pair programming at all, unless you are sure that the task is too complex to be solved satisfactorily, even by 2 solo senior programmers.